will give you a brief theoretical introduction about Neutrinoless double beta decay, because this is the aim of our research in general, and this is also why I'm doing this work. And in particular, in the case in which we are not discovering Neutrinoless double beta decay, so we are interested in down selection of the isotopes, and especially in case of discovery, we need to improve nuclear models calculations. And in order to do this, it's important to keep a synergy between these models and experimental data that can benchmark these models. In order to take this new, let's say, high precision experimental data, we need a suitable detector. And I will show you that among the many that are there, one of the possible suitable detectors to do this is a cryogenic calorimeter. And then we show you two measurements that I performed using my PhD about this experimental data. So first of all, we can measure with a very easy experimental setup at LNGS, Laboratori Nazionali del Gran Sasso, the measurement of the half-life and the shape of India 115, which is a forbidden beta decay, and after I will tell you something more about this. And for the first time, we could fit simultaneously both the spectral shape of the decay and also its half-life, matching the few of the expectations coming from the theory. Then another example, quite similar. So in this case, measurement of half-life and shape of the two-neutrino double beta decay of tellurium 130. And since this is a quite rare decay, you can easily understand that this measurement is way more complex. So this has been done within the CUORE experiment framework that is searching for Neutrinoless double beta decay in tellurium 130. So to start, Neutrinoless double beta decay. So this is the Feynman diagram. You have neutrons becoming two protons and ejecting two electrons only, no neutrinos. And this is possible only when there is a virtual exchange of a Majorana neutrino, so neutrino and anti-neutrino, they are the same from the wave function point of view. So if you can observe this, you're actually assessing Majorana nature neutrinos. And this is also very helpful to constrain both Majorana, the neutrino mass hierarchy and also the absolute scale. And it's very important for the standard model, for beyond standard model searches, because it's an example of L-symmetry violation process. Usually, the experimental signature is a monochromatic peak at the Q value of the reaction, because we usually absorb both the electrons that are coming out from this decay. And you want to measure this peak, you have always an avoidable background, which is the two-neutrino double beta decay, which is a second-order standard model process that is happening. Actually, it's a standard model process that represents a huge background here, as well as other backgrounds that are coming from the experimental setup. So it's very important to keep background low, a good energy resolution, because you want to disentangle the peak with respect to the other backgrounds that are usually continuous. And then, since this is a very, very rare decay, we are putting limits. We're talking about 10 to the 25, 10 to the 27 years. You want to have a large mass, so a large experiment that you want to run for a very long time with a high efficiency. Okay. Now let's come to the physics part. Let's say you can write the half-life of the decay in this way. This is the real experimental observable. So this is related to the experimental performance. The better the experiment, the longer will be the half-life you are sensitive to. And you can write this depending on what you are interested, the parameter of interest, which is the what we call effective Majorana mass, which is just a particular sum of the different neutrino masses. So in the case of a positive signal, you can measure this, and if you know these numbers, you can actually compute this. And this is the real probe to the beyond standard model physics. So this is just an example. This can be also written in other ways, but it's important to understand that this is what we want to compute. But in order to do this, we need to know these numbers. And these numbers are related to nuclear physics. First of all, you have the phase space factor, which is mainly related to the kinematics of the decay, and as for now can be computed within, let's say, relatively low uncertainties and low approximations. While the other part, which is this one, is let's say, include the matrix elements. Matrix elements are, in some sense, the they encode how the decay is undergoing through the different energy levels of the nuclei of the decay cell. And therefore, it's a very complex many-body problem that tries to compute these numbers, but in order to do this, you need several approximations, and you are many times limited also by computational time. There are lately some computation ab initio calculation of this, but still these can be done only for very light nuclei, while the main isotopes that are probing Neutrinoless double beta decay are quite heavy. So germanium 76, tellurium 130, xenon 136. So they are quite heavy, so it's still not possible to have these calculations. The result is that you have a very large variation, so very large uncertainty on these numbers, even within the same isotopes among the different nuclear models that are taking different approximations. I wrote this part in this way because I wanted to put the attention on this part, which is the axial coupling, which is to the fourth power. So a very, let's say, tiny uncertainty on these reflects as a big uncertainty on the half-life. And this makes complex both the calculation of this and beta-beta and also the isotope down selection when you are not actually seeing the Neutrinoless double beta decay. So that's what I just said. And the fact is that predictions, actually measurements, so measurements of the axial coupling, these can be done very precisely measuring the decay of the neutron. Are measuring this number. So the axial coupling for them is 1.27. But experimental evidences when studying or looking at the beta decays or beta-beta decays, so trying to match also the half-life to what to expect, are requiring a quenching of this number, okay? And in some theories, this quenching is even strong. So GA can be also be less than 1. And notice that here I'm writing GA effective because this is not that GA is different for these decays. It's a phenomenological renormalization of this number because theories are approximated. So it's a way to, in some sense, probe and estimate how a theory is far from the perfect description of the decays. The possible reasons, as I was saying, are due to the approximation, so limited model space in the various nuclear models, or also the correlations that there can be between all the nucleons inside the an atom that are not always included in the calculations. So one way to improve this is to improve the theory, to invent new ways to these calculations, but at the same time, I think it's important to have a data-driven improvement of the theoretical models, and this can be done with precise measurements of physical processes that are similar to the Neutrinoless double beta decay. So we cannot see the Neutrinoless double beta decay, so we do what we can with what we have. So we look at processes similar to that. Which are these processes? There are double charge exchange reactions. The beta-beta decays are one of these, for example, and these studies can be done, for example, accelerating ions against nuclei, or this can also be done. This has been done in the past at the meson factories when you could produce a lot of pions that were then impinging on a target, and you could study the emission of the target. Then you can also go for ordinary muon capture. So you have a muon that is captured by a nucleus. So it's a reaction between the muon and proton. There is an exchange of a W, and it comes out a neutron and a muon neutrino. And this is important if this is similar to the double beta decay because it's a double charge exchange. This is important in a different way because in this case, in these reactions, the momentum exchange is in the order of 5100 megaelectron volt. And it's also the very same range of what happens, or what would happen in the Neutrinoless double beta decay. And this is different from beta decays and double beta decays that we see and we can measure, because in that case, the momentum exchange is at least 1 order of magnitude lower. So studying ordinary muon capture, it's very important to study how the different energy levels of the intermediate nucleus of a double beta decay are accessible or not. And then we have beta decays, in particular beta decay shape. As I will show you, you can measure the shape of forbidden beta decays. Why? Because usually the shape of a beta decay is fixed mainly by kinematics, because there is only one nuclear matrix element that is important. But it is not true anymore for forbidden non-unique beta decays. In that case, dependence of the shape on the nuclear description is way more complex. So it happens that the shape itself is strongly dependent on the value, for example, of GA, of the axial coupling. So you measure the shape, and from that you can compute the axial coupling. And okay, this is even more important when there are different nuclear matrix element contribution that compete. And this is actually this is valid for equation like this. You have different nuclear matrix elements, and the vector axial coupling here, the vector axial matrix element is actually similar in absolute value as the sum of the axial and the vector one, but with a different sign. And this destructive interference makes the shape parameter, let's say, of the decay to be very, very dependent on GA. And in this case, I will show you a measurement in which we're using this spectral shape method, where let's say the model is dependent on GA, but also an additional free parameter, which is called small nuclear matrix element. And if GA is more, let's say, is encoding the shape of the decay, the SNME parameter is encoding the half-life. So it is readjusting the half-life of the decay. And then, okay, after you will see. Something very similar can be done with double beta decays. So always, also in this case, you have a contribution that is larger than the others, but in the late years, some improved description of the decay actually has shown how other contributions at lower levels can be important and can encode, also in this case, the value of the axial coupling from the shape. And we will do something similar. Obviously, in order to be sensitive to GA, you need to be very sensitive to the shape. In order to measure them, you need a reliable detector, a suitable detector to do this. You want an excellent energy resolution because you want to measure precisely the shape. You usually want a relatively low threshold because some of these shape effects are mainly focused how to say, the low energy part of the spectrum is more dependent on the shape effects. It would be good to have a single technique that can probe and measure different isotopes. And then you also want to maintain the detector systematics quite low. So you want to measure a shape. And in order to do this, you would like to have the source inside the detector, because if the source is outside the detector, you have additional systematics due to the, for example, to the dead layer of the detector, or to affect similarities. And among the different detectors, one choice can be low temperature macro calorimeters. Okay, very briefly, low temperature calorimeters are usually composed by two components. An absorber and a thermal sensor. In this case, I will speak about temperature sensors. You usually have a particle passing through the absorber, releasing energy. This makes this energy transforms into a spectrum of phonons, and these phonons happen to heat up the crystal. And the heat up is let's say a temperature pulse like a rise, like you see here. And this temperature can be measured by temperature sensors that are attached to the crystal. These absorbers are usually crystals, so you can grow them with the isotope of interest inside, and this allows for high efficiency and low systematic effects due to the detector. And the fact that you are operating these detectors at very low temperatures makes the energy resolution relatively good, quite good, let's say. But at the same time, since everything is thermally connected to a duct, and you need to wait for the pulse, for the temperature rise to go back to the base temperature, these are relatively slow detectors, so they are not suitable for high rate applications. But this can also be, they can anyway be used. Temperature sensors, there are many different temperature sensors. Here are just a few examples. You just exploit physics parameter that is changing with temperature. For example, if you're using MMCs, you have that the magnetization that you want to measure is dependent on the temperature, while for TES or LTDs, you have that the resistance of the device itself is changing with the temperature. If the first two are relatively fast, and first one has an easy calibration, the second one can be multiplexed when you want a very high mass, so a large array of detectors. The last one is the, let's say, easiest to use because it's can be read out with quite easily, let's say. But it's characterized by a lower thermal response, a slower thermal response. Okay, so let's go on. First measurement, indium 115. As I was telling you before, indium 115 undergoes beta decay, and it's aqua beta decay. And this measurement has been done within this, the ACCESS project. ACCESS stands for Array of Cryogenic Crystals, Evaluate Spectral Shapes, has been published by the European Union. And the goal of ACCESS is to measure the shape, precisely, the shape of different beta decaying isotopes, among which there are also some of the important for nuclear physics for the reasons I told you about before. So the easiest to be measured is actually indium because it's characterized by, let's say, a relatively high Q value and high abundance, natural abundance, so it doesn't require enrichment to have a good rate of signal. We have also technetium-99 activated crystal now that we are going to measure soon. And then there are anyway other possibilities. Regarding indium 115, before the measurement, we performed a design study. And so we found that the best crystal size is around 7 millimeters. And this was a sort of optimum between the signal over background ratio that reaches a maximum for lower dimensions and the total absolute signal rate, which just grows with the dimension of the crystal. And since the expected rate for a small crystal like this is not so high, we actually went for germanium LTDs, which are slow, but anyway, they are very easy to be operated, and they are okay, suitable for this measurement. Okay, this is the experimental setup. As I told you before, this is a very easy experimental setup. We actually did it with our hands. It was quite easy. There is a crystal, an NTD glued on top. There are gold wires bonded for the readout. And this has been done, the setup has been anchored to a dilution refrigerator at the Gran Sasso National Laboratories. It's an underground laboratory, so no muon background. The detector is this one and has been operated at around 16 millikelvin. There is a downside here. This cryostat had a relatively thick lead and copper shield, and we didn't have strong enough calibration sources to be used for the calibration and then taken out for the background runs. And so we decided to go for a permanent thorium-to-fission source. This is a thoriated wire that stayed there for the entire measurement. We took data for around 100 hours. The analysis is quite simple. You have some quality cuts that you want to, for each thermal pulse that you are triggering, you want to estimate the energy, which is in the end what goes in the final energy spectrum. We do this with the optimum filter. Optimum filter is just a way to maximize the signal to noise ratio in this case. Then we apply some other data quality cuts and pulse sheet cuts. And in this case, we needed to take particular care to apply constant efficiency cuts with the energy, because you don't want to introduce in any way some distortion to the spectral shape, because you want to measure the shape of the spectrum. And this is an example. So making cuts on the rise time of the pulse, which is just the time that it takes the pulse to go from the 10 to the 90% of the maximum. We needed to take care, so we didn't do constant cuts, but we did something like this. So keeping, for example, 2 sigma of the distribution inside. And this has a constant efficiency with energy. This is a spectrum that we took. As you can see here, there is a huge hump, which is the beta decay of indium. And then you see other lines, which are due to the thorium-232 source. Overall performance were quite good, and energy resolution with a maximum of around 4 keV at the peak of lead-212 here, and an energy threshold of 3 keV, and overall cut efficiency of around 50%. This is not so high, and the cut that was the most, let's say, prominent cut here is the one of the pileup. So we are just, what we do usually is to trigger a thermal pulse, open a time window around it, and we exclude all the windows that contain more than one pulse. And this is the result. So the efficiency was not so high, but it was anyway. Then the fit. Obviously, if you want to study the shape that is here, you also want to really study in details also the background. And you can do this with a fit, and you need templates. So we went for a Bayesian template fit with the sampling has been done with a Markov Monte Carlo. And you have signal templates that are coming from theory and from 3 different models. And these templates have been calculated for a grid of values of the axial coupling and the small no-grammatics element. So axial coupling that is making the shape to vary, and the small no-grammatics element that is making the half-life to vary. And as you can see, as I was telling you before, for forbidden beta decays, the shape is really changing a lot, while the GA is changing not so much. So we are very sensitive to this. The background template is mainly thorium-232 from the source nearby, and many other backgrounds such as from the materials, from the bulk of the materials, and activation backgrounds, and also backgrounds coming from the cryostat have been verified to be negligible. We have developed John Monte Carlo simulation of the setup, and we also process the Monte Carlo in order to introduce some detector effects, such as the energy resolution, which varies with energy, or the indistinguishable pileup. That means that this happens when 2 pulses are too close, and the time distance is lower than the time resolution of the pulse. And so the 2 pulses are actually seen as a single pulse, and the energy is the sum of the 2. Okay. The first attempt was what we refer to as best fit, which is the simplest thing you can think about. You let vary both the 2 parameters, and you try to see which is the best shape that matches the data. Okay, here you see the results. This is just one of the examples. And let's say that the data reconstruction is quite good and quite happy. If you see the residuals, they're mainly inside the 2 sigma band. Here you see the results in terms of number, different models. We have this GA. As you can see, the GA among the different models are quite different, and this is expected because different models are using different approximations. This will be more important after, but the important thing is that the physical parameter is compatible among the different measures and the different nuclear models, so the different shapes. Then we went for something a little bit different. So we actually want to benchmark a model. And so we don't want only to find the best shape, but we also want to match the measured half-life with the one that is calculated from the theory. So what we did is not anymore a fit by varying the GA and the SNME, but fixing this parameter, making different fits, with this parameter fixed, finding different GAs, and we find all these are fits with the SNME fixed. And then we actually can compute the half-life, and from the theory, you have an ellipse of a distribution of the half-life in this parameter space. So the half-life depends on these 2 parameters, and where you expect to find that half-life that we have measured. And in the end, what we did was to find the best match between these fits and this theoretical prediction. And the results are reported here. You have the best fit approach and the matched fit approach, and we call this matched fit approach. Important things, GA in the 2 cases, while fixing the model, is always compatible. So this should, in some sense, demonstrate the reliability of this process, of this, let's say, of how we are tackling the problem itself. The half-life also in this case are quite compatible, apart from this match fit of the QPM model that is always characterized by also characterized by a very bad chi-square, at least with respect to the others. So it's probably less reliable, and this model is not really able to match both the half-life and the shape. So something needs to be adjusted there. Apart from numbers, what we did was quite useful also for other theoretical groups, because we actually measured the shape of the decay itself. So we have a shape and an uncertainty band, And this can be used by other groups to test their own models. So if there are improvements in for a certain model, they can actually go pick this data and benchmark their model. And this actually happened a few months ago. So there is a group that was trying to, with an effective Hamiltonian within the shell model, to improve the description of this decay. And since they're using effective Hamiltonian and they're introducing all the correlations between the parameters, they're actually not really expecting a quenching on GA, that I remind you is a phenomenological effect. They can use a spectroscopy to check the energy levels they are quoting. And also they can test with the hour shape and half-life, as well as the ones of the other isotopes, their model itself. So indium is here, these are our data, there are also data from other isotopes. And the results, let's say, that you can find also in this paper, is that there is a good match of the shape without, in this case, for this model, a quenching of GA. But at the same time, the half-lives are systematically underestimated of 50–60%. So there is still work to do in this sense. So for these other further high-quality data are needed, also because if you can see, the difference between the bare Hamiltonian and the effective Hamiltonian, which is the black and the blue lines, are quite tiny. So you really need high precision measurements. Okay, tellurium-130, another measurement. This is another way more complex measurement. Tellurium-130 undergoes two-neutrino double beta decay. Two-neutrino double beta decay is a second order standard model process, so we are happy we can see it. This can happen only for even mass number nuclei for energetic reason. And the half-life, and this is important, is in the order of 10 to the 20 years. And the one before was 10 to the 14 years. Okay, so you have a signal that is at least 6 orders of magnitude lower. And it becomes tricky to manage backgrounds and also the signal to expect. So for this, you actually need way more complex experiments. One of these is CUORE. Obviously, CUORE stands for Cryogenic Underground Observatory for Events, is searching for Neutrinoless double beta decay in tellurium-130. But since there is a lot of tellurium-130, we can do measurement of the two-neutrino double beta decay shape. It's using tellurium because of its natural high isotopic fraction. So it didn't require enrichment. And it's also characterized by a relatively high p-value, around 2.5 MeV. It's located in Gran Sasso. It's running smoothly since 2019. And it's, as you can see here, it's quite complex. There is a large structure around that is needed maybe to disentangle vibrations coming from the environment and the experiment itself. Here we have a really powerful dilution fridge that is cooling down the detector and all this region around, so which is about 5 tons of material down to around 10 millikelvin. This is the detector, around 1,000 crystals of tellurium dioxide. So for a total mass of 206 kilograms of tellurium. And these detectors are operated as low temperature calorimeters. And if you can see also here from the zoom, we have, okay, the structure is copper plus PTFE that are keeping the detector there. And we have glued on the detectors germanium LEDs. And so it's the same thermal sensor that I've used for the measurement of indium-130. Data analysis, in this case, is a little bit more complex, but the steps are similar. So you have quality cuts and energy estimation. This is just an example of what I was telling you before, so the optimum filtering technique. Here you look at just this left plot. You have the pulse, the thermal pulse in the time domain. The blue one is how we would see it, and the red one is the filtered one. And what happens is that if you want to extrapolate the energy, you will get a better resolution and a better signal to noise ratio by using the filtered one. This is happening just because the filter is weighting less frequencies with higher noise, something like this. Then you have pile shape analysis cuts. Our pile shape analysis, how to say, based on the principal component analysis. And so we are actually discarding pulses that are very different from the template pulse we expect. And this can be given by temperature or electronic glitches or also vibrations coming from the outside. And we keep pulses that are similar. So let's see. In the end, we have, in order to exploit all the different topologies that can happen in the crystals during a single physics event, we're using multi-site event typing. So we are defining multiplicity, which is just the number of crystals that are involved in a single physics event. So multiplicity 1 will be an event depositing energy only in one crystal. And multiplicity 2, for example, will be two depositions in two different crystals. And this is very important in order to spatially disentangle the different background components, because you can easily understand that contamination in the bulk of the crystal will likely deposit energy only in that crystal and will die there, for example, an alpha contamination or a beta. While if you have an alpha contamination on the surface of the crystal, part of the energy will go in the alpha particle, maybe in the crystal, but the recoil will be emitted on the other side, and this can go in another, will likely go in another crystal. And so this will be seen as a multiplicity 2. Okay, now we need to do the same thing of before, but in a more complex way. So we need to perform a fit, reconstruct the data, and extract information from the shape of the two-neutrino double beta decay. Okay, this can be done by developing the background model of the, let's say, the model of the data of CUORE. First step is identifying all the expected contaminants. This can be done by using screening campaigns that have been performed before the experiment, or using the experience coming from previous experiments. CUORE 0 was a demonstrator of CUORE, so it was a single tower of CUORE that had been around for 1 year. So important information are coming from that. And then you can actually look at the CUORE data. These are the CUORE data. This is the M1 data, so multiplicity 1 data. So single deposition in a single crystal. This is the gamma region, so before the thallium peak, which is at 2.6 MeV. And that is the end of the natural, let's say, the gamma natural contaminations. And there are many peaks here that have been identified, many other peaks in the alpha region instead, that are these ones. And from here, you actually write down a list of contaminants that can be situated in different locations of the experiment. Then you need to define the fit model. We are actually trying to explain the number of counts in each of the bins we are using for the fit as a sum over different background sources that are modeled with Monte Carlo simulations. And a background source is a contaminant in a specific location of the experiment. And all these background sources, all these Monte Carlo simulation need to be normalized to the data, and this can be done through the fit. So actually, these are Monte Carlo simulations. These are the fit parameters that can be retrieved by maximizing the likelihood. This is our likelihood. We have a Poisson distribution over each bin, which is I. So we have a product over I. And you also have a product over K. K is the so-called target spectrum. In fact, we are actually doing a simultaneous fit of several different spectra that are not only M1 data. And this is done by considering around 80 background components. So it's quite complicated to run this fit. And then after having done this, you can perform the data reconstruction that I showed you later. But coming back, as I told you, each background source is modeled through a Monte Carlo simulation. So we have a Geom4-based application, simulation of the CUORE experiment. This is just to show you that we actually produce all the details, especially close to the detectors of our experimental setup. These are parts of the contaminants we are considering. Many of them are considered bulk contaminants, so they are uniformly distributed inside the materials. Can be the crystals or the copper close to it, or the shieldings, etc., etc. Some other contaminants are modeled as surface contaminations, so they are not uniform in the volume, but they are mainly on the surface. So we are assuming different exponential profiles for the activities of these contaminants. And we are also assuming different profiles with different characteristic depths. And this is done to try to explain the shape of the mainly alpha peaks that we see in our data. Then we have also external fluxes. Here outside there are also external shields. One made of lead, another one made for neutrons, made of polyethylene. But we are still anyway sensitive or limited by sensitive to the spectrum coming from the cosmic muons. And for this, we have a realistic simulation taking into account the initial energy of the muons and the rock profile of the mountain of Gran Sasso, so that we can simulate them reliably. After having done this, you run all this simulation, and as before, you process the Monte Carlo simulation in order to introduce detector effects. And in this case, this has been done in a very extremely detailed way, because we want to produce realistic CUORE-like data with this simulation. So we are introducing data taking effects. For example, we are defining during the data taking online very intervals, which are time intervals of high noise. Detector effects such as energy resolution, the shape of the gamma lines and the alpha lines we have inside the detector, and some analysis effects, for example, the pile up as before, the coincidence, etc. After having done this, okay, these are the target spectra, which I was thinking about before. So we have contaminants, and we are fitting different spectra. One spectrum is coming from the multiplicity 1 data. So one deposition in one crystal, you look at these events, and this is the spectrum of CUORE after 1 ton-year exposure. Then you do the same, trying to to build different spectra from the multiplicity 2 events, and you can do it in this way. So each event in multiplicity 2 will have 2 depositions of energy, one on the first channel and the other in the second channel, and you can represent this on a scatter plot. Then, in order to select different 1D spectra coming from this plot, you can actually select these bands that are associated to quasi-constant total energy deposition in these M2 events. And for example, here, this is the line whose total energy is 5.4 MeV, which is the energy of the decay of polonium-210. And by repeating this for all the different bands, you are actually you can project these bands onto one of the 2 axes and get for each band a 1D spectrum, which is something like this. So you take this, you project, and you have something like this, which is very similar to the multiplicity 1 and can be easily fitted. As I was saying before, 80 background components times 1 plus 44 M2 bands. So these are very complicated simultaneous fit. This is the, let's say, data reconstruction. After I will show you precisely how it is for the two-neutrino double-beta decay. But this is just to make you understand that we are able to, with this fit, to reconstruct all the backgrounds and to understand the source of this background. So you see in red, for example, is the spectrum due to the many different contributions of contaminants inside the crystals. You can see the muon spectrum here. You can see the spectrum due to all the contaminants present in the shields. And this is quite important because, first of all, you can estimate all the activities of all the background contaminants, but then you can also study the background decomposition in your region of interest. And in the case of Neutrinoless, the double-beta decay is around 2.5 MeV. And so we can do something like this. This is the total background in the region of interest of CUORE, and it's compatible with data, and we understood all the different sources of the spectrum. So we understand why we are limited and why not, and it's extremely important in order to think about the next generation experiments. Then you can do also other fancy studies, non-uniform contaminants inside the experiment, still important for next generation ones, time-varying backgrounds and stuff like this. Then coming to the two-neutrino measurement, we have actually done a fit optimization for these measurements. For this measurement, we selected geometrical subset that were optimal for this. We also optimized some other parameters, and this is the result. So you can see in blue the data, and in orange the data reconstruction, which is the sum of all the backgrounds. And as you can see, the data reconstruction is quite good. These are the multiplicity 1 data, and the residuals are these ones. while this one is just the projections of all the multiplicity 2 bands into one single multiplicity 2 spectrum, just because it's easier for visualization. And this is the reconstruction of the multiplicity 2. Also, in this case, it's quite, let's say, reliable. At least I'm happy about this result. So the fit is qualitatively relatively good, so 1.4, the reduced chi-square. And going to the fit of the two-neutrino double beta decay, so you need to imagine here from data, you can see there is this part that is the two-neutrino double beta decay to be sound to all the other backgrounds. We're actually fitting that part with the improved description I told you about before. So within the improved description of two-neutrino double beta decay, you don't have just one template for the shape of the spectrum, but you have actually several different components of the two-neutrino, and their ratios are important to retrieve some information for nuclear models. So this is the preliminary, and so we will let's say, confirm this. But here you have the results. So this is the, let's say, the most prominent one. You have other components here, and you can see also the uncertainties. Using the ratios and the absolute values of these, let's say, normalizations, or the normalization of these templates, you can actually say something for the nuclear models. So this is a plot in which y-axis there is effective axial coupling, which is the one we have also measured before with indium. And this is MGD3 is just one of the nuclear matrix elements contributions to the improved model of the two-neutrino double decay. What you can see from here in the data, and as you can see, the uncertainty are quite large for these measurements. Don't know if you noticed, but we don't have really an excellent signal over background ratio, because if you imagine that this is the two-neutrino, here you have a lot of background that is mainly due to the, thanks to the study, to the shields and to the copper close parts, close to the crystals, that could be really good to take out. And so the uncertainties are quite high, but the good news is that if this is compared with the theoretical predictions of different models, these two are coming from the Shen model, and these others are from QRPA, for the random particle approximation. All the predictions are, the predictions are compatible with the data we are measuring. And this is an analysis that is also has been run also from other experiments, for example, from Ranzen studying xenon and Cupid More studying molybdenum 100. And in general, all the measurements are compatible among them. So different experiments are actually finding something that seems okay, at least from the theoretical point of view. So this is still a preliminary, but soon probably will be out as a paper. So coming to the conclusions, was I fast or no? I don't know.
Very good.
Okay. So I hope to have convinced you that nuclear models are really essential to study neutrino double beta decay, both in the case in which of a discovery, because you want to compute the Majorana mass, and also in the case in which you are not really seeing the neutrino double beta decay peak, because it helps with the isotope down selection. So you can actually decide which is the isotope to invest money, because these experiments are starting to require a lot of money. Forbidden beta decays and double beta decays are precious benchmarks for nuclear main body problems. And this we have seen. So you actually measure with high precision these shapes, and you can benchmark and compare with theoretical predictions. And you can also help the nuclear models to understand where to tweak the model and try to see if you can improve something there. Low temperature calorimeters are among suitable detectors to do this, and they are particularly suitable, especially because they can be grown with different isotopes. So with the same technique, you can repeat the measurement the same way, maybe keeping into account all the systematics in common for different isotopes. And let's say the good news is that there is work from the theory side to develop these new, more realistic nuclear models. But there is also work in synergy with this experimental side to perform these high precision measurements that can be useful in this sense. And I think I'm done with this.
Much for the nice talk. We have time for some questions. Yes, you can start. Okay.
So, I'm trying to understand the result of your experiment on Indium 115.
Yeah.
Because when we introduced this question of quenching of GA, it was based on the half-lives. The half-lives on single beta decay and double beta decay are smaller than one would calculate.
Yeah.
Now, I do not understand how the half-life does not work, but the shape, it works. Now, what are the values of the initial spin and the final spin in this transition for Indium 115?
It's
because it, yes?
44 bitten. I don't remember exactly. I think it's 9/2 down to 1/2 or something like this. The spin. It's a 44 bitten decay. And yeah.
I mean, this is an important point to try to understand, because half-life is what determines GA, essentially. The shape was something that Eunice Honen introduced later.
Yeah.
I didn't check the calculation is correct.
In fact, there are, I mean, it's important, I think, this work, especially this work, is done by the group of Coraggio. And in this case, they're actually, by including two-body currents, they're really trying to explain without, let's say, without adding other free parameters that are needed to adjust, but they're really trying to explain from the, let's say, theoretical point of view, the shape, which is not bad, but still the half-life is not coming back. But at least the theory is not requiring the quenching. But yes, the half-life is still different from what we mentioned.
Okay, then the related question is, you mentioned something about being close to CBC, the conserved vector current, but that's for GA, for GB.
Yeah, yeah, this number, yeah, sure. Or maybe it can. What it happens is that, okay, GA is GA, and when you add this small non-chromatics element, you're actually losing the CVC assumption. So you are assuming that also GV is changing, and this is why you can both try to explain the applied current. But this is a trick. I understand your point, yes.
No, but this is a very good point, in fact, what we're making here, because there is the question of whether GB is also quenched.
Because usually the CVC is assumed.
We again mentioned that because while the conserved vector current protects GB for contribution, non-nucleonic contribution, it does not protect it from the other space that you're using. So GB could be renormalized, could be quenched as well. So your experiment is good because it says that maybe it's not so much, GB is not so much.
Yeah, some comments about this. First of all, one good news is that when we look at the results, you can actually have, okay, this is monochromatic segment that let's say is related to to GV, to how GV could be different from the CVC value, is always positive. It could be also negative, so more far from the CVC value, but it's always positive, so it's close to the CVC value, and this is useful to at least understand which part of the space to take. And we have also compared the small chromatics element computed with the CVC assumption, and the results is that, yes, they are not identical, but they are not so far. So probably the effect on GV is little, but it can have a great impact in explaining at least the half-life. But yeah, I agree with you. Yeah, Talia.
I also have a question about GA quenching, so maybe it's a good follow-up, which is just, does what no GA quenching means like change over time? Like, is there sort of, when you have, for example, your last plot, basically based on the theoretical calculations, meaning like, is there sort of an old theoretical calculation that people use as the basis and then said we calculate GA quenching relative to that? And then as people do new theoretical calculations, they say this is the new basis, or how does that tend to work? Because I think I've seen different plots and sometimes struggle to interpret like what are you talking about GA quenching relative to?
Okay, so let's say that in order to have a common ground, GA is this one, and we trust this one, which has been measured very precisely by several different experiments, also exploiting different techniques. So we trust this one. GA is this one.
Okay.
The point is that different models with different assumptions predict different GAs. I mean, predict is not the correct word. If you want to match these models with the observations, GA is different among the different models.
Yeah.
This is telling you that the different models are assuming different approximations, and the effect of this is the different quenching of GA. So GA is this one. The quenching is only phenomenological. It comes only when you compare the theoretical prediction with the data. And it's a sort of renormalization of the theoretical parameter because the theory is not complete. Okay. So this is, I don't know if I answered it.
Well, there is the paper, the theoretical paper that says we can match the shape without GA quenching. Are they saying they've predicted a different GA than this that matches the...
Yeah, it's not really predicting, but it's a sort of input parameter.
Okay.
The theory says, okay, if GA is 0.9, this is the spectrum. If it's 0.95, I repeat the calculation, and this is the spectrum. So it's not a prediction, it's an input parameter. And this can be measured by the experiment. It's only an input parameter.
Okay, okay.
Other questions? I wanted to, maybe we can have a little more GA discussion afterwards, but I wanted to ask you about access and what other isotopes are being measured and what we might learn from them and what the time scale is.
Let's say that related to the focus of this talk, these are the three isotopes of interest. This has been done. Actually, they will redo, I don't know if they they will redo another measurement with indium without the calibration source inside and with a TES on top, just to gain the 50% efficiency that was given lost because of the pileup. And okay, this is important because I don't know if you noticed, but I told you that the energy threshold is 3 keV, but if it is done from 80 keV. Why? Because we couldn't, we couldn't really model well the X-rays coming from produced by the emission, the particle emission of the source from the indium iodine crystal. Okay, here. The fit is actually done from here, but the threshold of the detector is here. Okay. And this, unfortunately, is given by the source inside. So we repeat the measurement with the source outside. Why is it important? Because here you actually have a very large dependence on the nuclear parameters. So if you can measure down to very low thresholds, you really can exclude or not a very big chunk of the parameter space. So this is for indium. Then another isotope is technetium 99. It's the physics case is actually very similar. And in this case, the F is very low, so you need a TS or an MC at least. And cadmium the same. So we actually, what you learn is just you do precision measurements from the experimental point of view, and then you try to compare the results with the theoretical predictions within different isotopes. Because the thing you would like is to have a theory that explains all the different isotopes and connects them. Because these can be also useful for Neutrinoless double beta decay, because we didn't measure the forbidden decay of Te-130. Then there are other isotopes that are of interest for backgrounds in neutrino physics or macro searches. So we actually noticed that many of the shape measurement, or at least the shape of many of the beta decays are not really precise measurement. There are, for example, also for potassium 40, which is everywhere, the last measurement has been done really decades ago. And so this is important because when you want to model the background of a certain experiment, if you know with precision the shape of these decays, this can help a lot. So we have in CUORE a problem with strontium 90, for example, argon 39 and 42 will be important for legend. So germanium studies of neutrino stability decay, bismuth is everywhere because it's a son of the lead-210. And then you have also samarium and lead-210, samarium 151 and lead-210 here for cosmic neutrino background detection. There is actually a work with a project called the RESNOVA, which will detect supernova neutrinos with the cryogenic calorimeters. And here you have the problem that you need to model your background at very, very low energies. And these are some of the contributions. So these you can help. You can help to better understand backgrounds and to benchmark nuclear physics models.
And what's at the size of the crystals? You said it was like 7 millimeters.
The Indian one is 7 millimeters. Yeah.
So that was just optimized for pilot and background. So
exactly. Yes, it's here actually for a signal to noise background ratio and the total absolute signal, because we didn't want to take data for too long. Otherwise, we would have gone for a dimension.